Refractive index of a liquid. The refractive index of a material is a dimensionless number that describes how light propagates through a medium. When light moves from one medium to another, it changes its direction, that is, it is refracted. If I is the angle of incidence of a ray in vacuum and R is the angle of refraction, the refractive index N is defined as the ratio of the sine of the angle of incidence to the sine of the angle of refraction. Here, we are using a convex lens to find the refractive index of a given liquid by parallax method. Theory: when a convex lens is placed over some drops of the given liquid on a plane mirror, a plano-concave liquid lens is formed between the lens and the mirror. If f1 is the focal length of the convex lens and f is the focal length of the combination of convex lens and plano-concave liquid lens, the focal length of the liquid lens f2 is given by f2 is equal to f into f1 divided by f1 minus f. If r is the radius curvature of the face of the lens which is in contact with the liquid, then the refractive index of the liquid is NL is equal to 1 plus r by f2. Materials required: the given convex lens, the given liquid water, plane mirror, retort stand, pointer, mercury, meter scale, china dish. Procedure: to find the focal length of the convex lens, the plane mirror is placed horizontally on the base of the retort stand with its reflecting surface upwards. The given convex lens is placed over the plane mirror. The pointer is arranged horizontally on the clamp of the retort stand, vertically above the lens. Looking from above, the height of the pointer is adjusted such that the inverted image of the pointer is obtained. The height is further adjusted so that the image coincides with the tip of the pointer without parallax. The image and object will be of the same size. The distance of the pointer from the top y1 and bottom y2 are measured. The average of these values gives the focal length of f1 of the convex lens. To determine the focal length of the combination of convex lens and liquid lens, remove the lens and place a few drops of the given liquid on the plane mirror. The lens is then placed over the liquid with its marked face in contact with the liquid. A plano-concave liquid lens is thus formed between the convex lens and the plane mirror. The pointer adjustment for coincidence is done and the distance from the top y1 and bottom y2 of the lens are measured. The average of the two values gives the focal length of the combination f. Then calculate the focal length of the liquid lens using the formula f2 is equal to f into f1 divided by f1 minus f. To determine the radii of curvature of the lens, the convex lens is floated in mercury, taken in a china dish and its marked face in contact with mercury. The pointer adjustment for coincidence is done and the distance from the top d1 of the lens is measured. The distance d of the pointer from the center of the lens is calculated using the formula d is equal to d1 plus y2 minus y1 divided by 2, where y2 minus y1 is the thickness of the lens. Then calculate the radius of curvature of the lens using the formula r is equal to f1 into d divided by f1 minus d. So the refractive index of the given liquid can be calculated using the formula NL is equal to 1 plus R by F2. Application: reflective liquid lenses are actually variable mirrors and are used in reflector telescopes in place of traditional glass mirrors.